Okay, I think we're ready to start. So today's webinar is going to be on hazard analysis and risk assessments of collaborative robots. Um, so this webinar is going to show the analysis of various hazards and ways to mitigate risk relevant to ISO 15066, which is a supplement and support to ISO 10218, which provides industrial robot safety standards, and this is going to specify more geared towards collaborative robots. This webinar is also going to provide an overview of the exSILentia HARA tool, hazard risk analysis, and how this is going to help us organize and find our risk associated with collaborative robot systems. So my name is Brad Hitchcock. I'm a safety engineer at exida. I work in both the OEM group, which does certifications of final elements, and I also work with the end users, where we'll be focusing here, includes the collaborative robots. I do gap analysis to make sure that systems are compliant with 61511. So exida helps our customers achieve safe and reliable solutions through just knowing the safety life cycle and our tools. So we use exSILentia to help us go through the safety life cycle and mitigate risk in systems. And we also work in certification. So as I said, working with final elements and making sure they're compliant with IEC 61508. So we're actually the clear global market leader in device certifications. As you can see, we have 2/3 of the pie. And we're also a global company. We work all over the world. Our headquarters are in Sellersville, Pennsylvania, and in Germany, but we have locations that are everywhere and do various needs in alarm safety, cybersecurity, and functional safety. Okay, so what is human-robot collaboration? So in our traditional industrial robot applications, you're going to have large barriers that are placed between a robotic system and the operator, and they have to shut off if a robot wants to enter the workspace, while the collaborative robot allows us to simultaneously be in the same area with the robot and just create better efficiency. So the objective is to combine the repetitive performance of robots, so just doing monotonous tasks that humans won't want to do or physically demanding for people to do, and it combines that with the precision and thinking of human beings. So collaborative robots in manufacturing will hopefully quadruple by 2025. So it's important that safety is in the collaborative robot is keeping pace with the growth of the industry. So here are some of the benefits of collaborative robots. So there's better robot-human interaction and efficiency. So during a normal industrial robot application, whenever human intervention is required, the entire production needs to stop for the operator to enter the area, while the collaborative robot allows us to interact, and this will reduce the human idle hours in production by 85%. In addition, it's suitable for small scale and mid-scale production. So the current industrial robots, they're mainly only used for the large scale production because of enormous costs that go into buying large pieces of machinery and the complexity that comes with setting up and adjusting these large pieces of equipment. So it's really only going to be used for manufacturing where the same thing is being made just all day, every day. But with the collaborative robots, they're easily set up and adjusted so that you can use them for multiple applications and are better for the small scale and mid scale production. So some more benefits of collaborative robots include it'll provide a safer work environment. So since ISO 15066 is it takes human involvement and collaboration in mind compared to ISO 10218. Everything is just checked extra thoroughly for safety so that the robots tend to be much safer than the industrial robots. Also, they're very easily programmed. So for the industrial robots, you're going to have some complex coding that goes into programming the robots. While the collaborative robots, they'll use teach pendant, which is basically you have a touchpad and with the touchpad, you're just gonna take the robot through different coordinates and the robot's gonna follow this when it goes in through its operation. And after that, you can change different speeds just so it's not going at the slow speed that it takes to program it at. Then there's also lead through programming, which is where the operator physically moves the robot to where the path of the robot needs to go, and it'll memorize that path and follow it. Last, there's greater flexibility in the human environment. So since you don't have these huge gates that are protecting the robots from humans, it frees up a lot of space in the workspace. Okay, so these collaborative robots, they're acknowledged to be very beneficial to manufacturing, but the question we need to really ask is, can they be safe? So here's an industrial robot application where a maintenance technician was inspecting machinery and a robot from a completely different section crushed the technician's head between a part in place and a new part the robot was attempting to load and killed the operator. So when a death in an industry occurs, just huge safety concerns are naturally going to come up, and it's important that these are addressed and that if they can't be fixed, then the production can't go on. Two very important distinctions that we're going to need to know about during this presentation when analyzing hazards and risk is the difference between quasi-static and transient contact. So in quasi-static contact, you're going to have an operator body part that is pushed up against a fixed surface by the robot or by any other moving machinery. And this will make it so the operator can't move away from the hazard. There's like a threshold, if it's more than 0.5 seconds that the operator can't move, then it's considered quasi-static. While transient is when the robot arm is going to hit the operator in free space and the operator can immediately get away from the hazard. So the importance of this is in quasi-static applications, the tolerable pain threshold, we're going to talk about those later, it's going to be half as much as the transient. So it's very important that quasi-static contact is avoided at all costs. So before we get into hazards and risk, we're just going to kind of go through some definitions. What is a hazard? It's a potential source of physical injury or damage to the health of people or damage to property or to the environment. And a hazardous event is an event that may result in harm. And what is risk? So risk is just going to look at your likelihood and consequence of an event, and when you multiply those together, you get your overall risk. And so this is important with safety risk, so an operator being harmed, environmental risk, which is less important in robot applications than many of the others we look at. And then there's business risk, so if this part breaks, will it affect business? How much business loss will there be? So in ISO 15066, there's 3 different types of robot-related hazards that we're going to go through in these next couple of slides. So there's robot-related hazards, there's hazards related to the robot system, and application-related hazards. So to go through these hazards, we're going to use this example robotic system to kind of demonstrate all the different hazards. So in this scenario, we have a pick and place application where both the robotic arms are going to be picking up these boxes. You're going to have two arms, two operators. The small one you see that's in the back over here, that's going to be a rubber suction gripper. So we'll talk about it more later, but it's going to be a softer material, more rounded edges. And the operator here is going to be in the area for about 90% of the time. So he will be consistently working with the robot. Meanwhile, the large robotic arm is going to have a metal clamp gripper, and he's going to only be in the area about 10% of the time. So he's not working with the robot nearly as much. So first we'll talk about these robot-related hazards. Robot-related hazards will include the robot characteristics, so load, speed, force, momentum, torque, power, so how much force is going to be exerted on the operator. As you can see, this large one here, we'll say this large one has 3 times as much force that can be generated from it compared to the smaller robot. So therefore, there's going to be much greater hazard or risk probability, or much higher risk because of the consequence being much higher for the hazard. Then we also have to look at the geometry and surface and the shape of the material. So as we said, the top one here, the small one, is going to be a rubber suction gripper, and because of that, okay, so that's more with the end piece. So these, we'll say, are like round arms, so they'll create a larger surface area, which will definitely decrease the risk involved. Because when you do look at the pressure, it's very important to look at the pressure of these, and when you increase the surface area, you're going to decrease that, obviously, force over area. And then, so going back to the quasi-static, making sure that there's no quasi-static conditions in this robot. So operator location with proximity to the robot. So the top operator, not very close, but he'll be working with that conveyor belt, it seems like. So you definitely have to take that into account. Maybe his arms and hands will be very close to the robot. And the guy on the bottom, he's not nearly as close. So that's definitely good in a risk sense. Next, we'll look at the hazards related to the robot system. So this is going to take into account the end effector, which I briefly touched on. So you have the metal gripper on the bottom is going to have, seems like it's going to have sharper angles and a harder material. So that's going to increase the risk compared to this suction gripper on the top. So then you also have to look at operator motion and location with respect to the parts. So is the operator with a conveyor belt on the top, how much is he going to be, how close is he going to be with the robot, and how often is he going to be right next to the robot? Fixture design, so maybe looking at that conveyor belt and any hazards can be involved there. Again, transient and quasi-static, that's going to keep coming up because it's very important. Location or design location to any manually controlled robot guiding devices, and influence and effects of the surroundings. Okay, and then so our last robotic hazard is going to be the application-related hazard. So we're going to look at process-specific hazards, limits caused by the personal protective equipment, and ergonomic design. So maybe you're going to look at surrounding processes, so welding splatters, maybe there's something, a process going right next to it where there's could be like some sort of projectile coming from there that the operator needs to worry about. And then also the personal protective equipment. So maybe these looks like a blue suit is maybe restricting the operator's motion, and that could potentially bring up more hazards. All right, so defining hazards through task identification. So task identification is where you're going to work with the end user to identify additional hazards that can come up with the specific task that's being performed by the operator and how much he's going to be exposed to the robot. So collaborative task can be characterized by frequency and duration of the operator presence in the collaborative workspace. So we said earlier that the guy next to the large robotic arm is only going to be there 10% of the time. So that'll greatly decrease the risk compared to the guy next to the small robot who's going to be there 90% of the time. So that definitely needs to be taken into account when you're looking at risk. And then, so this is also the frequency and duration of contact. So if they're in the area but they're not actually touching the robot, then that can also have an impact on the risk associated with the robot. Transitioning between non-collaborative operation and collaborative operation. So are they on their way into the workspace? Is the robot system still going to be working? Because that could provide more hazards that maybe on their way to the system they could potentially be harmed. Then automatic or manual restart. So if you have a manual restart, that could be just like an extra safeguard that could help mitigate the risk of the robotic system. Tasks involving more than one operator, so it's just extra risk that can happen naturally when you have two operators in the same area. And then additionally, human error with two people working together, maybe they create risks with each other. And then any additional tasks within the collaborative workspace. Okay, so now we're going to talk about power and force limiting. So often you're going to want to, through controller design, you're going to want to limit the amount of power and force that can be in the robotic system, taking into account the various contact that can occur, taking into account what body parts will be exposed to, and what kind of contact situation. So you have these three contact situations. You have the intended contact situations, incidental contact situations, and failure modes that lead to contact situations. So right now we're going to kind of briefly touch on these three. So the intended contact situations, they're going to be part of the application sequence, and they're naturally going to be designed to be safe. So you might not need really any safeguards for those because you know they're going to occur, and ahead of time you already design it so that it won't create a hazard. Then you have incidental contact situations. This is where human error is going to come into play. So safeguards to avoid these would be using the force limiting so that when the contact situation occurs to an unintended body part, that it's not a significant damage. Then you can have automatic shutoff after contact. A lot of robots are going to be designed so that it'll immediately detect when it hits a body part or just another object, and the robot's going to immediately shut down. And then last, you can enhance operator training procedures so that you can hopefully avoid this human error as much as possible. And then lastly, we have failure modes leading to contact situations. So this is going to be either a mechanical or a controller error, and it's going to result in contact with the operator. So to avoid these, you're going to want maybe a mechanical integrity program. So that'll be the making sure that the mechanical components are not worn out and they're not going to fail. They're not going to have random failures that happen, or at least you can decrease the risk of this happening. And then you also might want to review the controller code so that the robot doesn't go out of spec and do something that is unintended. And last, you're going to want procedures to keep the operator in the area only during dedicated collaborative work phase. so that when these do happen, they don't actually impact the worker or injure the worker. All right, so now we want to talk about risk reduction when with robot contact. So you want to consider the following for potential contact events: exposed operator body regions. So you want to, at all costs, you want to eliminate the possibility for the operator being struck in the head or the face area. And when you're looking at different body parts, we're going to talk later about biomechanical limits, and so different body parts can tolerate a certain amount of forces and pressures. You also want to look at origin of contact events, so where are they occurring, and probability or frequency of occurrence. And then you want to talk about quasi-static or transient again, because that transient allows for twice as much of a tolerable force to occur. And then last, you want to look at contact areas, speeds, forces, pressures, momentum. So things that will increase the force and increase the consequence when a operator is struck by the robot or part of a robot system. All right, so steps to achieving robot risk reduction. So first you want to identify the conditions in which contact could occur. Then you want to evaluate the risk potential for such contact events. So you want to see the likelihood of each thing happening, taking into account human error, amount of time that the operator's in the area, and then you want to look at the consequence and the force that's on the robot. And so then you want to look at designing the robot in collaborative workspace so that such contact is infrequent and avoidable. So this is kind of before the robot's even operating. You want to make sure that it's designed with safety. And then last, applying risk reduction measures to keep the contact situations below threshold limits. So maybe changing your controller coding so that the risk is mitigated as much as possible. All right, so there's two different kinds of risk reduction. So we're going to touch on each of these. There's passive risk reduction, which addresses the mechanical design of the robot system, and the active risk reduction will address the control design of the robot system. So passive reduction, mechanical design. So you want to look at increasing contact surface area with rounded edges, smooth surfaces, compliant surfaces, because this will decrease the pressure that is on the operator, and will avoid like cutting. And so then you want to look at absorbing energy, extending energy transfer time, or reducing impact forces. So adding padding and cushioning. So maybe that rubber gripper design might be more effective than the clamp design if it's possible to use that in your application. And then deformable components and compliant joints or links. Last, you have limiting moving masses. So just kind of making the design simpler so that there's less hazards in the area and less hazards for the operator to pay attention to, so that they can acknowledge them and avoid them. Then we have active risk reduction measures, which is your controller, adjusting your controls. So we talked about force limiting, so limiting those forces and torques that are allowed in the robot design, limiting velocities of moving parts, so that'll influence the force, but it'll also influence the operator's ability to get away from the hazard. Then we have limiting momentum, mechanical power, or energy, so that's also has to do with your force. And then you want to look at using sensing to anticipate or detect contact. So a lot of times you can make it so that we talked about a robot being able to stop at impact of an operator or just another object. You can also design it so it'll detect an operator in the area and stop before the contact even happens. Then using safety rated soft access and space limiting function, so making the range of the robot arm smaller, so that there's just less of a radius for the robot to create a hazard. And then safety monitored stop function. Okay, so now we're going to talk about biomechanical limits criteria. So we kind of briefly talked about this before, and so then we'll go a little more in depth. And so these are limits based off of pain sensitivity of each body part. It'll literally list everything from your head and your ears and face to your feet. So it lists tolerable pain thresholds for each of these in both quasi-static and transient contact. So here's kind of just a little snippet of that biomechanical limits chart. And so you can see here, the skull and the forehead and the face are going to want to be avoided at basically at all costs, and that's why they don't really change anything for transient contact versus quasi-static contact. But when you get into the other body parts, everything from the neck down is going to be, the transient contact is going to be doubled for a tolerable pain threshold. So it's much more, you definitely want to see transient contact compared to the quasi-static contact when contact needs to occur. Okay, yeah, so these are based off of conservative estimates and scientific research of pain sensation. All right, so now we're gonna talk about the exSILentia PHA tool. So it's used by exida to perform the hazard analysis and risk assessments, and it'll just create a very organized list of all the hazards that are present in the robotic system, so that you can see all of the likelihoods, the consequences, safeguards, recommendations. So it effectively will just organize everything so you can look at your system as a whole and see where you can address risk and to reduce risk of the overall system most effectively and cost effectively. Oh, whoops. Yeah, so actually now I'm going to take you to the exSILentia PHA tool. So in this example, we're going to use the same, we're actually going to use the same system as we were using before with the small robotic arm and the large robotic arm, and all the same conditions I talked before with the operators being in the area 10% of the time for the large robotic arm, 90% for the top. All right, so yeah, so for the small robotic arm, we're first going to look at improper startup. So we have two different causes for improper startup, and there will be a configuration error that's going to result in the premature startup, or there's going to be an accidental error by the operator. So the likelihood of these, you're going to see a lot more of these with accidental startup by the operator, because you have to expect human error to occur. So we're saying that this is going to be 10 to the -1 to 10 to the -2 per year, which is, you could even go even higher than that, considering it's a decent likelihood of an operator starting up the system. While the configuration error, we're going to say it's down one magnitude, 10 to the -2 to 10 to the -3 per year. And we're going to say the same consequence occurs for both of these. So minor injury to the operator in the area, and they're going to have the same severity. So we're going to say that's going to be recordable injury. So maybe like a hand gets pinched, but we're not going to say there's lost time because of this. And as you can see, the risk for the accidental startup, because it's a lot more, it's like more likely by a full magnitude. So we're going to say the risk is much higher than that of the configuration error. So we're going to compare this to the large robotic arm improper startup. So the likelihood of those is going to be the same because it's the same cause. But the consequence is, we're going to say that the severity goes up to a lost time injury, because as we said before, we're going to say there's 3 times as much force that's going to be exerted on this robot. So you could see maybe like potentially a bad bruise or even a broken hand. And so that'll increase your risk by a good amount. It'll go from to 16 and 14 from 8 and 3. All right, so now we're going to talk about, we're going to go to crushing. So this has 3 different causes. We'll just talk about this top one because I wanted to use this one just to talk about safeguards and recommendations. And so the cause is going to be hand trapped between the robot and the conveyor belt while the operator is removing a lodged part. So you can see operator, like a lot of times you'll have parts stuck in a conveyor belt and an operator's natural instinct will be to try to remove that. So we're going to give that a likelihood of 5. And the consequence will be we're going to see quasi-static impact between the robot and the operator's hand at maximum speed. So it's kind of like a worst case. And we're going to say that's a 3, so a lost time injury. And so it's going to be a pretty high risk. But you can see here we have safeguards. So we're going to say that the robot has force limiting configurations resulting in a safety fall after 25 newtons of force on the arm. There's also going to be a robot designed to minimize sharp edges, and the operator is only going to be in the area during dedicated collaborative work phase. So for this one, it's actually the operator only in the area. Since we said it's 90% of the time, that's not going to be as big of a risk reductor. So after that, you can also add recommendations for additional things that can be added to mitigate the risk. So this could be a review of the personal protective equipment used by the operator, maybe adding gloves to further protect them, and then increasing employee training on the robot operation. So these are just like additional things that you can like suggest, and right now they're open, but you can say that they're assigned or ready, approved, ready for peer review, or closed. So the last deviation we're going to talk about is misuse. So we'll look at this one, application of robot system outside of design spec. The load is above the maximum limit. So you can see here there's going to be 4 different consequences, and this one's actually going to include business consequences. So the first one is going to be increased wear out of mechanical components, and that's going to be we're going to see a business consequence out of this. The business consequences tend to be a lot lower than the safety. So just to get a 2, you need $50,000 to $500,000 in damage. So just having this 2 sort of implies that we're maybe replacing the entire robot just to create a risk of 8. And then for the business, you can also include safeguards, and the safeguards are a lot of times the same one as the safety safeguards, just because having a mechanical integrity program will improve like the wear out of the components, but it'll also improve the safety of the operator. Same with personnel training on operating procedures. And then there's no recommendations right now, but obviously you can add recommendations onto that. Okay, and then so the last thing I'm going to show you on the exSILentia is I'm going to show you a risk matrix. So this will show you can kind of adjust these values to be tailored to your system, and you can see that the ones over here, so when you get a risk score of 20 to 30, those are gonna be like high priority, and you're gonna want to address those before you even start operating the system again. While when you get into these orange, it's also high priority, definitely wants to be addressed soon, but once you get down into the green, it's lower priority, but they definitely are things you want to address. Same with the yellow, those are things you want to address, but you want to take care of these red ones first, and those will help you create the biggest risk reduction um, and just most effectively reduce risk of the system as a whole. So it kind of gives you a gauge of where your priorities should be with when you're trying to evaluate safety of a system. Okay, so that's it for the PHA tool. So now how can exida help with your safety needs? So we do robotic gap analysis. So we'll look at cybersecurity, functional safety, which is what we've been talking about, and it'll look at alarm management, and we'll kind of evaluate all of the hazards and risk as a whole and try to kind of give you a roadmap to how to improve the safety of the system as a whole. Then we have hazard analysis and risk assessment. So we do all different kinds of machine safety. So this was mostly focused on collaborative robotics, but we'll do it on also industrial robots and just any type of machine safety that's needed. Then we'll do functional safety assessments. We'll do SIL verification. We'll do FSC 110, which is our machine safety training. And then we have the exSILentia tool, which is what I took you through right there. Okay, so any questions right now? I think we're good on those. So yeah, thank you for everyone for attending this webinar. Definitely reach out to us for our latest information. Follow us on Twitter, Facebook, LinkedIn. Thank you again.